All right. So we're going to talk about a very specific shape of a distribution, that that comes up very often as a type of distribution that data fall into. And this distribution is unimodal and symmetric. So if we remember what those are, we might have an idea of what it's going to look like. You might have seen it as a kind of bell curve before. There's what it looks like. And so it starts to swoop up, and then it starts to swoop down, and then it's going to start to swoop the other way again. So it has this this nice bell-shaped curve to it. This is called the normal distribution. And if you're looking at a set of data, a group of data, then a lot of times it'll look like this bell-shaped curve. If it does, then you can say that the distribution is approximately normal. And the two main pieces that you'll need to know within a normal distribution are going to be the mean and standard deviation. So those are the two things that we're going to use to complete and make up the normal curve. All right. This is a model. So the normal model, the shorthand that we use to describe it, you'll see this occasionally. Usually you'll see it just written out, but occasionally you'll see n parentheses mu comma sigma. So this says that we have a normal distribution with this mean and this standard deviation. That's just shorthand for the normal distribution with that mean and standard deviation. So that just gives you directions for how to graph the normal curve. So let me label the normal distribution with a mean of, say, 10 and a standard deviation of 5. So remember, this is our mean, and this is our standard deviation. So if we have a mean of 10 and a standard deviation of 5, the mean of the distribution is going to end up being in the center. So our data is going to be centered right at the mean. That's the nice thing about a symmetric distribution. So that means if the mean is 10, then 10 is going to go in the middle. And then for our normal distribution, our scale, the scale that we draw it in, is going to be going by standard deviations. And so since standard deviation is 5, we're going to mark this off by 5s. So here is 15, here's 20, and then if I go back, this is going to be 5 and 0. So here's one standard deviation to the right, here's two standard deviations to the right, and then this is one standard deviation to the left, two standard deviations to the left of the mean. So that's how we would label and draw If I had a normal distribution with a mean of 10, standard deviation of 5, there's how you would draw it. You would draw your curve. That's how you would label your scale. Another way we can do this, if we wanted to scale and standardize this for any normal distribution, then we can mark it so that it's centered at 0 and just count standard deviation. And the thing that is centered at 0 and can just count standard deviation is z-scores. Oh, vocab terms. This is going to be more important in chapter 4, so don't worry too much about it right now. But just so you know, there are different symbols that we use for different things. So if the numbers used for the entire population, we're going to use the Greek letters of mu and sigma. These are called parameters. And then if it's from a sample, it's called a statistic. So the population is everybody we're interested in. The sample is the group of people that we actually got data from. And we're hoping to generalize from the sample to say something about the entire population. And the way we'll eventually remember it is that parameter goes with population and statistic goes with sample. So starts with a P goes together, starts with an S goes together. So what we're going to use is we're going to use z-scores to kind of standardize this normal curve. And keep it consistent where our mean is going to be 0 and our standard deviation is going to be 1. This is called the standard normal distribution. The standard normal distribution has a mean of 0, standard deviation of 1. And so here's a drawing of what the standard normal distribution looks like. So here's my normal curve again. Here's the center. We have the mean, which is at where? 0. And now each of our markers is going to mark 1 standard deviation. So here's 1, here's 2, here is -1, and -2. The other thing you'll notice about a normal distribution is that there's not a ton of extreme values out in the tails. Most of the data is packed near the center. In fact, in a normal distribution, since the normal distribution stays consistent, we can have basically markers for how much of the data we have around the center. And so this is called the 68, 95, 99.7 rule. And it's just a quick rule of thumb for you to remember how much of the data you should have in a certain amount. So we have a 68, 95, 99.7. Let me see if I can do this here. So there's my normal curve. Oh, it's right here. I'm going to be lazy and not draw it. Or I'll draw a simple version of it, and then we'll look at the more complicated version. So what this is saying is if we have 0, 1, 2, 3, -1, -2, -3. If I'm zooming in on just within one standard deviation of the mean, so one standard deviation to the right, one standard deviation to the left, that area is going to be 68% of the data, or 0.68 of the area. So 68% of the data is going to be between one standard deviation below the mean and one standard deviation above the mean. Then if I zoom out for two standard deviations on either side, the zone in between there, this is 95% of the data being within two standard deviations. And then the end of our rule is that if we go out to 3 standard deviations, I won't try and shade that in, but within 3 standard deviations is going to be 99.7% of the data. The 68 and the 95 are what we're going to use most often. It's not exactly 68 and exactly 95. It's actually 95% of the data is like 1.96 standard deviations. So it's not quite 2 standard deviations. But if we want just a quick rough estimate, then that's going to give us a good quick visual of that. So let me show you, here's the more technical graph we can look at here. So this is mu plus sigma, so that's 1 standard deviation above. Here's 2 standard deviations above. And you'll notice that this is 34 and 34 because 68's on each side. Since it's symmetric, since we have symmetry, then it just divides it cleanly in half and we have 34 apiece. So this is about the amount of data that we have. So if you want to look at that and track that down for the examples that we're about to look at, that'll be helpful for you. All right, let's show some examples here. Okay, let me draw a picture. Can I give myself more space? A little bit. All right. Suppose that birth weights of newborn babies are approximately normal with a mean of 7.6 and a standard deviation of 1.3. So the first thing I want you to do, if you haven't done it already, I want you to try and sketch the normal curve and label the scale that you would use. And usually what you're going to do is you're going to label the mean, and you're going to label 2 standard deviations above, 2 standard deviations below. That's usually going to be your scale for the normal distribution. Here's where we put the mean. What was the mean? 7.6. And then we're going to go 2 standard deviations above, 2 standard deviations below. So if we're going a single standard deviation above, that's going to be what? 8.9. Right? We're going by 1.3 since that's our standard deviations. So add another 1.3. 11, 10.2. 10.2. Then we want a standard deviation to the left. 6.3. 5.0. All right. What percentage of babies will weigh less than 8.9 pounds? Oh. Probability that X is less than 8.9. Here's where our probability notation comes in. X is less than 8.9. So I want 8.9 is right here. There's my 8.9, and I'm going to shade everything to the left. I want everything to the left. Another way you can think about this, if I did a z-score, the z-score here, well, would be 8.9, the value, minus the mean of 7.6, over the standard deviation, which was 1.3. What's this going to come out to be? 8.9 minus 7.6 is going to be 1. Which you should have been able to tell me because this is 1 standard deviation above, and that's what the z-score is measuring. Should have a z-score of 1. So we're 1 standard deviation above, and we want everything to the left. So let's look here. So we're starting here. We want everything to the left. I will undo that so that you can actually see it. There we go. So total, we have 68 here. And we've got 13. This is going to be 16. So 68 and 16 is going to be 84. Is that right? Did I add correctly? Okay. So we add up all the area that's to the left of this, and we're going to get 84. So this is 0.84. So 84%. Probability that X is greater than 8.9. So if I have 84% of them being less than 8.9, what percent are going to be greater than 8.9? It's going to be 16. We're going to take 100 minus 84. Or 1 minus 0.84. 16%. It would be this area. Everything to the left there. What percentage will weigh more than 5 pounds? This is where my diagram is going to start to get cluttered here. I might draw a new diagram after this one. Probability that X is greater than 5. So mark your 5. And I want everything to the right. I want everything more than 5. So go ahead and tally up. This time we're starting how many standard deviations to the left? 2. We're starting here, everything to the right. Total it up. What do we get? It's 97.5 if you add them all up. %. The other way you can do that is by saying, well, I want, just like I had the 100% minus the 84 that we had already found. So we took 100%, subtracted off the 84 that we found. We can go the other way too and say, well, I want everything to the right. Well, right now there's 2.35 and 0.15 is going to be 2.5 to the left. So I want everything except the 2.5% to the left. So I'm going to take 100, subtract off the 2.5% that I don't want, and be left with the 97.5% that I need. So sometimes it's more helpful to subtract off the area that you don't want to get the area that you do want. So sometimes that's going to be quicker. Okay. So that's my 68, 95, 99.7. Is using these to get that. What's the z-score here for 5? Don't plug in numbers yet. Z-score for 5. How many standard deviations to the left? Was it? It was 2, right? 1, 2 standard deviations to the left. So that means the z-score is not 2. 2 is over here. -2. Because it's below the mean, so when we take the value and subtract the mean, that's going to be negative. And you can check this yourself. So that would be 5 minus 7.6 over 1.3. And you can plug that in and check that it's going to be -2. Questions on that so far? All right. So the only numbers that we're ever interested in are the values that are right on the standard deviations. And we don't have to worry about any other numbers ever again. So there are only 1, 2, 3, 4, 5 different numbers that we're allowed to use, and we can't use any other numbers ever. Okay, I'm kidding. That would be not very useful. Because what if we wanted the proportion of babies that weighed less than 8 pounds? So let's draw our normal curve again. We had 7.6, we had 8.9, we had 10.2, we had 6.3, we had 5. So one of the things you should do on these problems is to draw a picture. because a picture is going to help you get a visual of how much area there is. So, for example, if I centered it at the mean and shaded the area to the left, how much is that going to be? How much should that area be? If I go to the left of halfway across, then that should be half the data, 50%. So 0.5 should be your answer, or 50%. So that should be 50%. So if the area there is greater than that, then we should be looking at more than 50%, and our answer should be above that. So it can help give you a number sense of what the answer is and a number sense of where the value that we're looking at is. So go ahead and give an estimate of where 8 is in this normal curve, and then shade everything less than it. So everything less than 8. It should be between 7.6 and 8.9, yes? Is it closer to the 7.6 or the 8.9? Should be closer to 7.6. So let's go around here. That's about where 8 is. And we want to shade in which direction? Left. What percent was less than 8.9? What was to the left of 8.9? It was 84, right? Okay, so should our answer be more or less than 84? Should it be more or less than 50%? More. So now we have a little bit of a number sense of what this answer should turn out to be. How are we going to get to our answer? We're going to use z-scores. So what is the z-score of 8? It's going to be 8 minus 7.6 over 1.3. So we're going to use that z-score and then find the probability that z is less than this value. That's the beauty of the z-scores, is that it allows us to standardize and be able to say everything to the left of the z-score for the normal distribution is this amount every time. So z-score gives us a standard that we can find the areas and the percentages of every single time. And we'll talk more about how that's going to work tomorrow. Homework. I'll get page number in just a minute. But it's going to be 41 through 51 odds. (54 through 59 all). On page, let me find it while we get the desk sprayed down here.